Hello everyone, welcome to another Root Labs at lunch. My name is Bart Moens, working for Data Roots and facilitating the Root Labs at lunch. So normally, if there is no semi-lockdown, Root Labs organizes in-person events to share knowledge about applied artificial intelligence, and you can find more info on the Data Roots Root Labs website. Today we have Noel is going to do a session around dimension reduction techniques or data compression. So should you have questions, there is a Q&A which is open for questions, and at the end we have planned some time to go through these questions. Okay, Noel, so you can start.
Yeah, okay. Do you hear me well?
Yes.
Okay, so hi everybody. So this presentation will be a bit technical. So the idea is to talk about different machine learning methods to do data compression, or in the machine learning world, we call this sometimes dimensionality reduction, but it's quite the same. Okay, let's start. So basically, first let's ask the question, what is data compression? So the idea of compressing data is to reduce the data into less data, but with keeping the same information, or at least reducing information the most as possible. So what are the interests of this? Basically, the first one is to store more data in the same space. So then you can save resources, so money. And another application can be to transmit more data. So basically, if you want, for example, you're a streaming platform like Netflix, you want to transmit your information. You will not transmit all the information of the video. First, you will compress the video, then send the compressed data, and then decode the compression version. And there is another use case for machine learning, especially. Usually in a machine learning model, you have different features. Sometimes you have too many features. And the idea is to reduce this number of features because of a phenomenon that is called curse of dimensionality. So I will not go into detail, but basically the idea is that if you're increasing the number of features in your model, then you will need to increase almost exponentially the number of data that you will use to train your model. So that's a problem. And that's why you want to compress your data. So the idea in this presentation is to show 4 different methods, machine learning based methods for data compression. And let's start with the most basic one that you maybe heard about if you studied a bit of intermediate statistics, which is PCA, Principal Component Analysis. So the idea is that you have informations. So for example, you have different features for a flat. So the surface area, the number of windows, the distance between this flat and the city center, this kind of stuff. And you would like to reduce those information, so those 7 information into 3 information by using the correlations between the features. So basically, if you have, let's say 1 window, you have 10 meters square, you have 2 windows, you have 20 meters square, you can see that there is a linear correlation between those ones. So you can use this correlation to reduce the number of variables because you just need 1 variable to store those 2 information. So basically, PCA will do this job, will find the best linear combination between those features to reduce the number of features. So if you want to visualize a bit how PCA is working, you can visualize it as a projection of a high dimension space into a lower dimensional space. So here, for example, on the picture, you can see that you have a 3D space. And basically, PCA will just project your 3D space into the best plane, into the best 2-dimensional space here. So what is PCA used for? Usually in statistics, you will see it to visualize your data set. So PCA is mostly used for visualization, but what you need to get is that visualization is just a consequence. It's just an application of the compression. But basically, PCA will just compress, and with this compression, you can visualize. Okay, what you need to remember is that it's a linear compression. So as I said, for example, as I said, like if it's linear correlation, it's okay. But if, for example, you have an exponential correlation, so basically here you have 1 window, you have 10 meters square, you have 2 windows, you have 100 meters square, you have 3 windows, you have 1000 meters square. Okay, it's not that realistic, but it's just an example. Then your PCA will not be able to take this correlation into account. So basically what you would like is a non-linear compression, and the best non-linear compression nowadays are autoencoders. So that's the second method. What is an autoencoder? So basically it's a particular type of neural network. And the idea is that you will give your data as an input, and you will train your model to rebuild the same input. So the same input. So you would wonder, so what's the point of doing this? If you just give as an input an image, for example, and you have the same image as an output, what's the point? The idea is that you will have in your neural network, in your autoencoder, a bottleneck. And because of this bottleneck, the autoencoder will need to learn how to compress this information. So in this case, it's an image, this image into 2 variables. So basically this part, we usually call this the encoder, because you will encode your information into, in this case, 2 latent variables. Those variables in this layer are called latent variables in latent space. And then this part, which is the decoder, from those 2 variables, we'll try to rebuild the image, the initial image. So you can understand quite easily that the number of latent variables will have a huge impact on the reconstruction of your image, because if you just have 2 variables, it will be quite hard to rebuild the exact same image. So here you have an example of different autoencoders using different amount of latent variables. So here you have 2. You can see that. So this is the initial data set. You can see that with only 2 variables, the reconstruction is quite fuzzy. It's not that good. It's not really accurate. But if you increase the number of variables, 5 here, it's getting better and better. And here with 20 dimensions, with 20 variables, it's almost the same as the initial data. Okay, so this is about autoencoders. Just to make a link with the PCA, is that the autoencoder is just using the nonlinear parts. So basically, your nonlinear parts are the activation functions into in the neurons and the hidden layers. But if you remove those nonlinear parts in your autoencoder, so basically, if you just keep the input layer, you just keep the latent space, the latent layer, and the output layer, it will give exactly the same results as the PCA. So that was just to make a link between the autoencoder and the PCA. So what are the applications of autoencoders? So basically autoencoders are quite like a family. It's a bit like neural networks. You have different types of autoencoders, but in general, what are the applications of autoencoders? So the first application is like compressing. So as I said, for example, you can just give to your autoencoder low definition images and train the autoencoder to rebuild the high definition images. So this is for compression. Another nice application is denoising. So basically what you will give to your autoencoder as an input is the noise data that you artificially noise, and will teach it how to rebuild the unnoised data. And you have other application more related to generation. So basically here you have images that are missing some parts with like a white blank. And the idea is that you will give to your autoencoder those images, and it will learn how to rebuild this image. And the last one that is quite interesting. So if you were to the previous Root Lab session presented by Dorian, he talked about the Eurovision AI Song Contest. And basically the algorithm that they used for this Eurovision AI Song Contest is based on variational autoencoder. So for song generation, basically it can be used as well. So you have let's say two fields of application: compression and generation. That's a bit what you need to keep in mind. Okay, so autoencoders are super nice, but of course there are limits. So what are the limits of autoencoders? The problem with autoencoders is that if you don't constrain them, then you don't have any control on the latent distribution. So basically here, I put some examples. Let's say that you give images to your autoencoder. You will give one image. So let's say that your autoencoder is already built, is already trained, sorry. You will give one image and you will get those values for the two latent variables, okay? You will give another image. You will have two other new variables here, two new values, etc., etc. And then you can see that your distribution is quite random. You don't really know how the distribution is working. This is a problem. This is a problem mainly for one reason. Another one is more linked to regularization. So basically you don't want too high values because otherwise it will increase the variance too much. But the main reason is that if you use your your autoencoder, sorry, to generate new data, you need some values to generate this data. So basically what you will do is just take this part, the decoder part, and give a random value. So let's say 10, this one 20, and then you will see what the decoder will generate. The problem is that in this example, here you can see that all the variables that the autoencoder has seen are positive. But if, for example, you don't know what is the distribution, so you will give, for example, negative value, and then the reconstruction will not be as efficient because the autoencoder never saw negative values. So basically, you will not have all the patterns that your training data set got. So that's a problem. And to face that problem, people invented the variational autoencoder. So what's the difference between normal autoencoder and variational autoencoder? Is that you will add two layers in your structure. So one layer, so this is the latent space. This is the bottleneck that we have seen before. And before this latent space, you will get two layers. So one layer that is representing the averages of your latent space, your latent variable. So this one, for example, I think you can see my cursor. So this one is the average of this latent variable, this one of this one. And this layer is the standard deviation. So basically that's the same standard deviation. So this value is corresponding to the standard deviation of this variable, etc., etc. And from those two layers, you will just sample. So sample, it means just generate random variables based on some information. You will sample your latent space from those values. Okay, but so that's in a nutshell, what is a variational autoencoder? The thing is that if you don't change the loss, you will get exactly the same as an autoencoder. So what you need is to change the loss function. So this is the reconstruction loss that you have in the autoencoder. But if you add this term, which is minus the divergence, the KL divergence, I will not go into detail. But basically, if you add this term to the loss function, it will force your distribution to be close to the normal distribution. So the minus KL divergence is representing the difference between your distribution and the normal distribution. So basically, you're just forcing your autoencoder to learn to make this latent space into a normal distribution. And it's what you want, because normal distribution, you know a bit how it works. And if you want to generate new images, you just need to take a random value sampled from a normal distribution, and you will get structured data. Okay, so that's variational autoencoder in a nutshell. Of course, variational autoencoder is not perfect, neither. So what is the problem with variational autoencoder? The problem is that if you give too much latent variables, it will not be able to see that there is too much. So let's take an example. So here you generated different images based on only 4 independent factors. And the term that is super important here is independent. So basically the independent factors are the X position, so here, the Y position, the scale, so big or small, and the rotation. Okay, so you only have four independent factors to generate those images. If you give if you train a variational autoencoder with 10 latent variables, basically the compression will be done on the 10 latent variables, but it's not useful because you only have 4 independent factors, and it's where comes the disentangled variational autoencoder. So that's a bit the state of the art in data compression using neural networks. Is that basically, so what changes with the variational autoencoder is that you will just add a term here, hyperparameter. There will be kind of a trade-off between the reconstruction and the correlation between the features, let's say. And so if you're using a disentangled variational autoencoder in our example instead of a variational autoencoder, what you will get is that only 4 variables are used to compress your data. So the model just guessed that there are some variables that are not useful at all to store because there were correlation. So basically, it's a really nice way to get independence, like the best compression that you can get. So you specify a value of beta. I will talk a bit later about how you do that. And basically, you can see here that if you analyze the different variables, so for example, the Z5 is really corresponding to the Y position. The Z7 is corresponding to the X position. This one is corresponding to the scale. And okay, there are 2 variables that are, let's say, taking the rotation component. I don't know why 2 actually. Maybe because the rotation is not that independent, like requires 2 variables. I don't know. Okay, so that's a bit what disentangled variational autoencoder can do. So why this is quite promising, why is it super interesting, is that it increases the model explainability. So nowadays, there are a lot of companies that don't want to use machine learning models because they don't know where the results come from. They don't really understand. This is a nice way to explain a bit how those images were compressed, for example. Another pro is that the disentangled variational autoencoder, that you can also call beta variational autoencoder, seems to be robust to noise. So if you just add noise in the real life, you just have noise all the time, it's robust to this. And the problem that is really underlined by the authors of the paper. I didn't mention it, but this disentangled variational autoencoder was invented by the Google laboratory DeepMind, and they're really careful. They're really saying in the paper that you don't need to take this as the perfect solution. There are some issues, so it's just promising. It's just super interesting, but it's not the solution to everything, because, for example, it can only work on continuous data. So here you just have continuous data, X position, Y position. But if you're using categories, it doesn't work. And another point is that the value of beta, so in our example it was 4, seems a bit arbitrary. So you just need to try different values, but there is no formula to guess this hyperparameter. Okay, so before letting you ask me some questions, I just wanted to show you another example of the applications of the disentangled variational autoencoder. So basically the same team, they were working on a reinforcement learning project, and their agent needed to compress the different images from a video game, and they used the disentangled variational autoencoder. And what they did is to generate new images, they just were varying just one variable. So not different variables at the same time. They were taking the latent space and just changing one variable at a time. And what is super interesting is that you can see that if you just change one variable, it will just change one parameter, one independent parameter. So here, for example, if you just change the Z4 variable, you will just change the distance to the object. Here you have, for example, for the Z2, you turn on the left if you're just changing one variable. Here you have the room ID, so the texture is a bit changing. Here the object ID, etc., etc. So that's quite interesting because it's a bit a way to understand how all those data were generated. And here you can see that with a normal variational autoencoder, it's a bit fuzzy. If you change one variable at a time, it will change different parameters. It will turn on the left and change the distance at the same time, etc. Okay, so hope you will learn something today with those 4 different approaches. So if you have any question, don't hesitate. Of course, it's an overview. I didn't go into details for some topics, but of course, if you have any question, don't hesitate now to ask.
For now, there are no questions, Noel.
Okay.
Seems like you've explained it pretty clear.
How does the model train on the okay, wait. How does the model train on type of images will work on other types of images? So basically, if it's trained on one type of images, it cannot work on other types of images. Huh? Of course, your training data set needs to be to have the same structure as the testing data set. So basically, if you're giving like, I don't know, just pictures of cats, and then you're testing your model on dogs, will not work. Yeah?
So we have a question in the chat as well.
Yep.
Is there good material available to get familiar with these types of models?
Good material, yeah, I guess. I think if you just type variational autoencoders or disentangled variational autoencoders on the web, you can get some articles. Of course, if you really want to understand everything, how everything is working, you can read the research papers. That is really interesting. It's quite hard to read, especially those ones. But yeah, you can just Google it. Huh? That's the solution to every problem. Okay, on the slide, sorry, okay, another question. On this last slide, is the vertical axis the beta? No, it's not. It's the value that you will change. So basically, if your variable was like 0, if you change the variable to 1, let's say, the image generated will change. And this is the consequence. So basically here is not the beta. The beta is fixed. And what will change is just the value of the latent variables. Okay, another question. Will this be useful to compress video streams, for example, if the model needs to be trained on similar types of data? Actually, I don't know. I don't know how big streaming platforms are working. Netflix, I don't know which algorithm they're using to compress their data. I don't think that they're using those type of methods to compress their videos. And yeah, so I'm not sure that this can be applicable to, at least nowadays, to videos. But actually, yeah, maybe, yeah. I don't know. And there was another question, no, in the conversation. Okay, that was not a question. That was a compliment. Thank you.
Okay. Okay, so yeah, I think that we're also 25 minutes in the webinar. So yeah. Thank you, Noel, for hosting this interesting webinar. It will also be on the YouTube channel. So if you have any questions, you can post them as well in the comments on the YouTube channel.
Okay. And I can answer.
Yeah. Okay. Thank you all for joining.
Thank you. Bye-bye.